Hey, my name's Walker with Goat Tutors, and today we're going to learn about derivatives, their definition, and some practical applications in about 9 or 10 minutes. So, first thing I want to talk about is slope. So, as I'm sure you know, the slope is just the change in output of a function or the y values over the change in input of the function or the change in x values. And so slope is pretty easy to find for linear functions. You can just take any 2 points on a line and just find how y changes with respect to x. But for curves, it's a little more complicated. So one way we can sort of approximate the local slope of a curve, like obviously you can see curves sort of, the slope changes as we go along the curve. So here the slope is more severe, and then it sort of levels out and becomes like less and less sort of severe. So one way we can sort of approximate that is with a secant slope. So we can take 2 points on the curve and draw a line between them, and then we get an okay approximation for, like, let's say the middle of these 2 points. Like, this gives us an approximation of this. And so I have these two x values, x and x plus h, and then these two outputs, f of x plus h and f of x. So that gives us like an okay approximation of this, the slope of this point right here, or like a tangent slope. So a tangent slope would just be the line that goes just through that point and no other point. It just touches that point and nothing else. So to get a better approximation, we can make the gap between x and x plus h smaller. So as you can see, if there was a point in the middle of these, it would be much closer to x and x plus h. So this would be a better approximation of like a tangent slope. And we sort of use this idea of like a secant slope in our definition of the derivative in calculus. So the tangent slope of a function is basically just the secant slope, but it's a secant slope as this value h approaches 0. So effectively, that's going to give us the formula for the rate of change or the slope of curve. And if we want to find the slope at any point, we just plug in for whatever the input to our function is, and it'll give us the rate of changes. So one example or application of this is from kinematics, which is sort of a branch of physics that deals with describing how objects move. So it says that the velocity of a car from t is 0 to t is 10 in meters per second is 2t squared. So given that, what is the acceleration from t is 0 to t is 10? So the relationship between velocity and acceleration is that, acceleration measures, how fast something is speeding up or slowing down. So it's effectively the rate of change of velocity, or the derivative of velocity. So it would be really, really easy to solve this if velocity was a linear equation. If it was just 2t, then acceleration would just be the slope of 2t, which is just 2. But because it's 2t squared, it's a non-linear function. It's something with a curve. We actually have to use the derivative to solve it. And so, yeah, we're going to use the difference quotient. And yeah, if we plug in this 2t squared into our difference quotient formula, we get the limit as h approaches 0 of 2t plus h squared minus 2t squared over t plus h minus t, which is the same as the limit as h approaches 0 of 2 times this whole trinomial minus 2t squared over h. We can multiply, we can distribute this 2 and then combine like terms, and we get the limit as h approaches 0 of 4th plus 2h squared over h. And then thankfully this h cancels out. This is pretty necessary. If your h doesn't cancel out, you probably made some algebraic mistake, and the reason it's necessary is because if we still have an h in the denominator, we try to take a limit, we're going to get something that's undefined, because effectively we'd be dividing by 0. And if we cancel the h out, divide everything by h, we get 4t plus 2h as h goes to 0, which equals 4t plus 2 times 0, because effectively the limit as h approaches 0 of 2h is just 2 times 0 or 0. So we're given that 4t equals acceleration with respect to t. And from there, we can pretty easily solve what acceleration is at t is 5. It's just a of 5, which is 4 times 5, which is 20 meters per second squared. And the reason it's meters per second squared is because velocity is in meters per second, and acceleration is measuring the change in velocity per second. So it's meters per second, which is, if you simplify, it's just meters per second squared. So this second example is from economics. This is a bit of a lengthy word problem. So if you want to pause it, read the problem, and then we can get started. Okay, so the first thing it's asking us to do is find p prime of x, the marginal product of labor. So this notation p prime just means the first derivative of p of x. This is a pretty common notation that you'll see more and more as you start taking more and more derivatives. So we want the derivative of 9 root x, which is our production function. That's the same thing as 9 times x to the 1/2. This is just a different way of writing square root of x, but for our computation, it makes it a bit easier. And I'm going to use what's called the power rule here. This comes from the difference quotient, but it saves you a lot of time. If you want to know why this works, you can kind of play around with different polynomials in the difference quotient, or just look up a proof that uses the difference quotient. They're pretty easy to follow along with. But if not, basically the way it works is that you take the initial value of this exponent and you bring it down as a coefficient multiplied by your original coefficient. And then you subtract a whole number 1 from the value of the exponent. So effectively, we'd be getting 9 times 1/2, which is 4.5, x to the 1/2 minus 1, which is x to the negative 1/2. So this is equivalent to 4.5 times 1 over x to the 1/2. Because negative exponents just means put it in the denominator, basically. Or 1 over root x. So that's the marginal product of labor. So part B asks, is hiring an additional worker profitable? Is it worth it? So to answer this question, we need to think about what is the marginal product of labor telling us. So the production function tells us, given a number of workers, what is the amount of output we're able to produce. So the marginal product of labor, or the derivative of that, would basically be telling us, as our number of workers changes, which is the input of the production function in this case, how does our output change? In other words, if an additional worker is added, how much output will they add? So in order to find this, basically the problem says we have 5 workers. So if we hired an additional worker, we'd have 6. So we're going to put in 6 to our marginal product of labor equation to find what is the additional, or in economics we say the marginal product that this 6th person is able to produce. So that's going to be 4.5 times 1 over the square root of 6, which is approximately 1.837. But we're not quite done yet. We need to find sort of the value in dollars that adds. So these Sonic the Hedgehog themed pencils are selling for a pretty steep $3 each. I guess they're popular nowadays. But if we do $3 times this marginal product, which is 1.837 approximately, we get approximately $5.51, which, if you look at the wage you're going to pay your workers, is less than that $6 that you're going to owe this 6th additional worker. So from this information, we can conclude that it is not worth hiring a 6th worker, because basically they've added $5.51 in additional revenue, assuming that all your pencils sell, but you have to pay them $6. So effectively, you'd be losing about 50 cents. This is not worth it. So yeah, that was some practical application of derivatives, as well as a brief overview of the difference quotient, how derivatives are defined. So yeah, I hope that's helpful.